Okay, so what are ligands? This is probably a word that you've never met before in your life until you did A2 chemistry. But a ligand and complex chemistry is, I mean, complex in terms of a complex and what a complex is, not complex as in hard, obviously. But ligands and complex chemistry is usually brand new to us, even though actually there's a lot of complex chemistry in our immediate environment. One of the examples, which we will look at briefly, is hemoglobin, for example, which obviously is a huge part of every human being and lots of other animals or versions of it in animals as well. So what are these? You do need to know definitions. They could ask you definitions. So definition of a complex ion is a metal ion surrounded by ligands that are attached or bonded through coordinate or dative covalent bonding. You can use either of those words. Your exam boards do prefer one over the other, so just have a quick flick to the bonding instructor part of the specification and see whether your specification calls it coordinate or dative. They should accept both, but they do have preferences. A ligand is an ion or molecule that donates a pair of electrons to a central transition metal in a coordinate or dative bond, or via a coordinate or dative bond. So here we have got our central metal ion, and here we have got 6 water ligands. And that makes up a complex. Central metal ion and the ligands around it. If we have a look at what this is going to look like, let's get blue. If we have a look at what this is going to look like, we have got our central metal copper and 6 waters. Now, technically, it is the oxygen that donates the lone pair of electrons to the bond. So I'm going to draw the oxygen pointing towards the central metal ion. And I'm going to draw my bonds as arrows because that's how we like to denote. Sorry, my pen's a little bit skewiff there. That's how we like to denote coordinate bonding. Oh no, I can't make this neat. I'm going to try and make it a bit neater. Right, that one's going that way. That one's going that way. That one's going that way. And that one's going that way. So water, 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 water. Ooh, that was a bit funny. Let's try that again. Water, lone pair, lone pair, lone pair, lone pair. There we go. 6 water ligands surrounding a central metal ion. I'm going to do that one again because that looks a bit rubbish. Usually, in the same way we do with our ions, when we're drawing out dot and cross diagrams, we usually put a bracket around it. It tells us that everything can be considered together. Oh, that just says O there. It should say H2O, sorry. Usually means they can be considered together. In this case, the overall charge is +2. And we'll think a little bit about how we can work out what the charge is in a minute. What's the coordination number of this structure? And how do we determine coordination number? This has a coordination number of 6 because there are 6 coordinate bonds, not because there are 6 ligands. And I've just realized that also just says O as well. Oh dear, there we go. It should all be waters. Let's just triple check now. Yes, we're all good. It's to do with the number of coordinate bonds, not to do with the number of ligands. So the coordination number is the number of coordinate bonds or dative bonds that are formed between the ligands and the central transition metal, specifically around the central transition metal. That's the key for me, is looking at it, not paying attention to how many ligands there are, but how many bonds are being made, because it's independent of how many ligands. What else was I going to say? Let's just put a note in that this is coordinate/dative bonds. Okay, lovely. Let's think about some specific ligands then. A ligand must have at least 1 pair of electrons to form a coordinate or dative covalent bond. because that's how the bond is made, one atom donating a pair of electrons to a covalent bond. So they must have a pair of electrons that are available to donate. There are some ligands which only donate a single pair of electrons per ligand. These we call, let's just change the color back to blue. These we call monodentate, mono as in monodentate, mono as in monocle, single glass for a monocle, or monorail, single rail. So mono meaning one, monodentate, single dentate, single coordination. So each of them have the ability to donate a pair of electrons. For water, oxygen obviously technically has 2 lone pairs it could donate. It only donates one of them. Chlorine technically has 3 lone pairs it could donate. It's only going to donate one of them. You're not going to get a single atom that's able to donate 2 electrons to different places on a central metal ion. So a single atom, even if it does have multiple lone pairs it could donate, it's only ever going to donate one. Because if you think about a pair of electrons, they're both negatively charged. You try and have another pair of electrons next to it going in the same direction, you're going to get repulsion happening. So they're only ever going to donate one each. Our carbon actually carries the lone pair of electrons in a Cn- ion. Even though we often call it Cn-, it's actually the carbon that carries the minus charge. And ammonia, nitrogen has got that lone pair as well. What about some bidentate? Then there's a couple of bidentate ligands that we might want to be aware of, specifically 1,2-diaminoethane. Have a quick go at drawing that if you aren't confident with your structures. What's it going to look like? 1,2-diaminoethane. Well, if it's ethane, there must be 2 carbon atoms making up the main carbon chain. And it's ethane, so they're singly bonded, so they'll both have 2 hydrogens attached as well. And 1,2-diamino means there are 2 amine groups, 1, 2, one on each carbon. Whoops. So you've got NH2, NH2. That means both of those nitrogens have got a lone pair of electrons that they can donate to a bond, to a coordinate bond. Also, the ethanoate ion, C2O4 2-, has got 2 lone pairs of electrons on 2 of the oxygens that it can donate. And benzene 1,2-diol also has got the oxygens, 2 oxygens in the diol that can both donate a pair of electrons. So these can donate 2 pairs of electrons. These are bidentate, bi as in bicycle, 2 wheels, bidentate. And finally, oh, there's a slight error there. That minus should be up the top. EDTA 4- should be up the top there. It's obviously formatting has meant it's fallen down. But EDTA 4- has got a 4- charge on it, but there are 6 pairs of electrons available to donate from it. So just have a quick look. Where are those pairs of electrons? Well, each one of these negatively charged oxygens has got a lone pair of electrons. It's very willing to donate. And the nitrogens have got a lone pair of electrons they're willing to donate. So that's 6 pairs of electrons. Technically, there are more, but this is how EDTA will coordinate. And because there's more than 2 pairs, we can call this polydentate or multidentate. You will see it written as both, poly meaning many, like polymer, many monomers, or multi, as in multiple, multidentate. Polydentate or multidentate. Let's keep going. I think, yes. So ligands, multidentate ligands will replace monodentate ligands around transition metal ions due to this thing called the chelate effect. Now, I don't think it's named as the chelate effect in all specifications, but it is an entropic effect, and so technically everybody could be expected to understand it as a process because it's just entropy. It's an increase in entropy, okay? So although you may not have looked at this specifically, I think, and it's not specifically on the OCR specification, I would pay attention to it because it is still important and it does still, it is still something that you could be asked, I think. It's just you might be given a little bit more support with the context. So multidentate ligands will replace monodentate ligands and bidentate ligands as well, technically, around transition metal ions due to the chelate effect. What this is, for example, here we've got 6 monodentate ligands, and we can replace the 6 monodentate ligands with 3 bidentate ligands using the chelate effect. Our bidentate structure is going to be more stable than our, no, sorry, let me rephrase that. Our complex made up of bidentate ligands will be more stable than a complex made up of multidentate ligands. No, monodentate ligands. I'm really sorry, my words are getting caught in my mouth. And also you're going to get an, wait, make sure I get it the right way around, an increase in entropy. And the world wants disorder. We tend towards disorder. More disorder equals more stability. Less disorder equals more instability. So we're tending towards stability and higher entropy and disorder. And that direction of the reaction has an increased entropy. Why? Why is there an increased entropy? Look at the number of molecules you've got. Here, we've got 4 total molecules. We've got our complex and 3 EN molecules. And then as a product, we've got 1, 4, 5, 6, 7 molecules. So there are more ways to arrange 7 molecules than there are 4 molecules, so it is more disordered. And this is called the chelate effect. The higher coordination numbers are entropically favored, and there is an increase in the number of arrangements of molecules in solution when monodentate ligands are released. We get more entropy, means that forward reaction is favored. It means these reactions happen favorably and what we're going to say easily. Was there anything else I wanted to say? Don't think so. Okay, let's keep going. We might as well just have a look at this one because it's a good way to consider our theory. This says, explain why a chloride ion is considered a ligand, but methane is not. How do we approach exam questions? First of all, let's think about the context. Context, I've seen ligand. If it's asking about ligands, it must be transition metal complex topic. So that's the topic that my brain is focusing on now. The command word is explain. So I need to give a reason why. And then specifically, I'm giving a reason why chloride ion is considered a ligand, but methane isn't. Why can methane not act as a ligand? That's my direction. So what are our thoughts? Well, if we're not sure, we could draw a diagram. And actually, if we do a well-labeled diagram, we could get marks from a well-labeled diagram. So we have got a written answer here, but I'm also going to draw some diagrams. What is a chloride ion going to look like? We have a diagram of a chloride ion. We've got 1, 2, 3, 4, 5, 6, 7, 8 electrons around our chloride ion. What about methane? Methane has got 1, 2, 3, 4, 5, 6, 7, 8 electrons around it, around the central atom. Why can it not act as a ligand then? Well, this is where our good labeling comes in. There are 4 lone pairs available for donation from chlorine. There are no lone pairs available for donation from methane. That would probably get us 1 mark, just that diagram. If we want the second mark, we need to explain that because we've been asked to explain, we need to explain that the lone pair is needed to donate to the central metal ion and allow it to act as a ligand. That's really where the second mark comes from. So in this case, we would probably need to do a little bit of writing as well, but we could get 1 out of 2 marks just by drawing that diagram. So, or we could just write a chloride ion has lone pairs that they can donate to a central transition metal, forming dative covalent bonds. A methane molecule does not have any lone pairs, so it is not considered a ligand. Lovely, 2 marks.